that are available to the two new expressions were also available to the old ones. That means that effectively we've reached a cycle. These two sides have stayed equivalent so far on the cycle by not terminating, so they'll continue to stay equivalent no matter how many more times that cycle repeats. Because of that, we can discharge this proof branch by coinduction and complete the proof. Now, evaluation on its own doesn't always give us the approximations that we want for coinduction. For a more complex example, let's take a look at this theorem. Take n x's plus drop n x's equals x's, where take is the function that returns the first n elements of a list, and drop is the function that returns all of a list except the first n elements. If n is a successor and x's is non-empty, we can do some simplification on the left-hand side. We can eventually remove the list heads because they're identical and move to considering only the list tails. And then at that point, it looks like we have an expression pair that should be usable for coinduction with the original expression pair. We have n prime and x's prime replacing n and x's in the take application, but in the drop application we have successor of n prime and x cons x's prime instead. This is an inconsistent mapping, so we can't actually use coinduction here. Note that we can't sidestep this issue by just doing a little more evaluation so we get down to reducing the drop application, because we're in symbolic execution. We could keep concretizing n with more successors and x's with more list elements, and if we did that, we would get stuck reducing the take application forever, and we would never reach the drop application to reduce it and find a cycle there. We need a different approach for that. And to handle issues like this, we introduce a novel system of generating, proving, and using lemmas to rewrite expressions to make them more amenable to coinduction. This system is fully automated and it's integrated into Nebula. When we try coinduction here and it fails, we notice that the true drop applications are the sub-expressions that caused coinduction to fail. So we carve them out and make a lemma out of them. The lemma is drop successor of n prime x cons x's prime equals drop n prime x's prime. On the right-hand side, we've replaced n and x's with n prime and x's prime because that's the mapping that we had for the take applications. Proving this lemma is trivial just because of the definition of drop. And once we've proven this lemma, we go back to the point where coinduction failed, we rewrite the newer state pair automatically, and we try coinduction again with the rewritten version. Let's see how that looks. When we apply this substitution, the new expression becomes take n prime x's prime plus drop n prime x's prime equals x's prime. With this substitution in place, we can make a consistent mapping from n to n prime and x's to x's prime between the old and new expression pairs. And that means we can apply coinduction here to discharge this proof branch and complete the proof. In addition to proving equivalences like this, we can also demonstrate that two expressions are not equivalent to each other. Whenever we do, we return a specific counterexample as evidence for the inequivalence. The obvious counterexamples are the ones where both sides' evaluation terminates, and they terminate with values that are distinct. The less obvious counterexamples are the ones where one side's evaluation terminates, but the other side's evaluation fails to terminate. We can catch these too, and for them, we introduce a novel system of detecting what we call cycle counterexamples during symbolic execution. If we ever find that one side's evaluation terminates, we start looking out for cyclic evaluation on the opposite side. What that means is that if a new state is at least as general as an old state on its same path, according to the definition of approximation, there's a possible execution path leading from that state that loops infinitely. We can see an instance of this with the self-subtraction example from before. On the right-hand side, we have z, which is a terminal expression. But on the left-hand side, we have m minus m, which we can keep reducing forever if we keep concretizing m with more and more successors. We notice this pattern as soon as we reach m prime minus m prime. By the definition of approximation, m prime minus m prime is at least as general as m minus m. That means that any evaluation paths that are available to m minus m are also available to m prime minus m prime. There was a path that led from m minus m to m prime minus m prime, so we can take that path again from m prime minus m prime to reach another expression pair that's also at least as general. And we can keep repeating this process forever to have non-termination. And since we have possible non-termination on the left and guaranteed termination on the right, these two sides can't be equivalent to each other. And we return the counterexample m equals successor of m as evidence for the inequivalence. One other significant implementation detail to note is our handling of symbolic variables of function types. We don't concretize symbolic functions in the way that we concretize symbolic variables of other types. What happens instead is that when we encounter an application of a symbolic function, we replace it with a fresh symbolic variable. If we ever see the same application multiple times over, we can reuse the variable from before, but we only do an exact syntactic equality check, so it's possible that we could make distinct substitutions for two applications that really are equivalent. And because of this, spurious counterexamples are possible when we're dealing with symbolic functions, but these are rare in practice. During our evaluation of Nebula, we never encountered a single one. More importantly, verification is still sound anyway, in spite of this possibility, because these substitutions only make proof goals more general rather than more specific. So we're still proving everything we need to prove, just more generally. Now we can step back and look at the main algorithm that Nebula uses at a high level. We alternate between running symbolic execution and attempting to apply proof techniques to the obligations that are generated by symbolic execution. If you look at the min inequality example from before, we start by branching on A, and then on B, we discharge a branch by the equality of those falses. Then on a different branch, we apply coinduction with the original expression pair. And we follow a similar procedure for all the other branches that you don't see on this slide. And we keep repeating this process over and over again until we discharge all proof branches, in which case we say they're equivalent, or we find a counterexample, in which case we say they're not equivalent, or we run out of time or hit a specified loop iteration limit, in which case we say that it's inconclusive. Now let's move to talking about our performance evaluation for Nebula. Nebula takes its inputs in the form of Haskell rewrite rules, which are constructs like you see here that assert that expressions of one format are equivalent to expressions of some other format. The Haskell compiler allows users to define their own rewrite rules, but it doesn't check the correctness of those rules before applying them, so Haskell rewrite rules are a good use case for our work. The specific equivalences that we formulate as rewrite rules are the 85 theorems that come originally from the test suite for ISAPlanner, which is a different tool. Their formulations in Haskell come from the code base for Zeno, which is a Haskell verifier that operates under the assumption that all expressions are finite and fully defined. All 85 of these theorems are true when we have that assumption of finiteness and complete definition, but when we generalize to the real non-strict semantics of Haskell, where infinite and undefined expressions are possible, only 24 of them are still true. Of those 24, we verify 22 and time out on the other 2. For the 61 theorems that are no longer valid, we find a genuine counterexample for every single one. For some additional evaluation, we look more closely at those invalid theorems, and we create modified versions of them that are true under non-strict evaluation. We make them true by imposing minimal requirements on totality or finiteness for the theorem's arguments. By totality, I simply mean that certain variables are forbidden to be concretized as bottom or to have bottom as sub-expressions. An instance where this is necessary is the take-drop example from before. N needs to be total because if N is bottom and X is the empty list, we get bottom on the left and the empty list on the right. To enforce finiteness, we rely on walk functions like what you see here on the right. A walk function is a function that iterates over the whole structure of an algebraic data type in order to force non-termination in the event that it's infinite. Walk_nat is an example of this. It iterates over all of the successors in a natural number and then returns some other argument when it reaches 0 at the end. We can use walk_nat to turn the self-subtraction example from before into a true theorem. If m is an infinite nat, then m minus m will run forever, but so will walk_nat mz. For the modified theorems that have totality requirements but no finiteness requirements, we verify 11 out of 18. For the modified theorems that have finiteness requirements and possibly totality requirements as well, we verify 12 out of 56. For the final part of our evaluation, we look at our ability to generate cycle counterexamples. Of the 61 invalid theorems that I mentioned before, 44 have counterexamples where only one side terminates. We can restrict ourselves to finding only cycle counterexamples for these theorems by requiring all of their arguments to be total. This rules out bottom counterexamples, and all these theorems are true under strictness, so that leaves cycle counterexamples as the only option. When we impose this restriction, we find a genuine cycle counterexample for 32 of the theorems and time out for the other 12. Now I'll move to talking about some potential directions for future work based on our work in this paper. The principal application that we foresee for our work is the verification of rewrite rules in production Haskell code. Hackage is the largest open source repository of Haskell libraries, and we found that hundreds of libraries on Hackage include rewrite rule definitions, so that's some fertile ground for applications of our tool. A different direction for future work would be to utilize Nebula to verify properties of Haskell functions like what QuickCheck does, except with actual logical verification instead of random test case generation. A third direction for future work would be the creation of a new tool based on Nebula that handles both strict evaluation and non-strict evaluation together at the same time. There'd be some utility for this because certain strict languages support non-strict data structures alongside their ordinary strict semantics. Examples include generator patterns in Python and lazy streams in OCaml. Having a tool that reasons about both strictness and non-strictness at the same time would give us a better understanding of the features of these languages. To wrap up now, I'll summarize the contributions behind our work. We introduced Nebula, which is the first ever fully automated expression equivalence checker for a non-strict functional language. Nebula relies on a novel, fully automated coinduction calculus for proving equivalences. To support that coinduction calculus, we introduced a novel approximation relation between expressions in a functional language. And also to support coinduction, we introduce a system of generating and using lemmas to support coinduction. And we also introduced a technique for detecting cycle counterexamples during symbolic execution. Best of all our work is open source, and it's available at this GitHub link that you see here. So thank you for coming to my presentation. If you have any questions, I can take them now. Oh, yes, the mic.
Also, this one works. So
Oh,
answer that.
This one, right? Yeah. Yep.
Really interesting work. So these transformations that you showed were not equivalent in Xeno. Are these necessarily bugs, or is this just
Wait,
a different?
you mean these or something else?
The ones that you found in Xeno.
These?
Yeah.
What's your question?
Okay. So are they bugs in the Xeno package, or is it just in the difference of they assume nothing is going to non-terminate?
No. They're not bugs in Xeno. They are true under the assumptions that Xeno makes. But we're considering the more general non-strict semantics of Haskell, and that's what makes them not true anymore.
Okay. Yeah. Thank you very much.
Are there any applications of your work outside of Haskell?
Well, this tool in particular specifically targets functional languages, and like I said, it would be possible to use the same techniques that we use in Nebula for reasoning about those non-strict structures in other languages like the generators and lazy streams. Although as Nebula is now, you would need to be reasoning just about those in isolation with no side effects or reference to the ordinary strict semantics of those languages. Does that answer your question?
Could you also apply this technique to help Haskell verification tools more generally, like as another form of automating, like checking like liquid Haskell refinement types or stuff like that? Since maybe you can reduce some of these proof obligations also to expression equivalence checking.
Yes, it could be usable for that same domain. Although I should add the caveat that if you want to prove arbitrary logical propositions using Nebula, you would do that by formulating the proposition as an expression and then saying that's equivalent to true. And a lot of the things that Nebula is designed to target, you would lose out on because you're looking at a situation where some function always reduces to a terminal expression.
So for the cases where you're not able to prove an equivalent, right? Have you considered adding some form of hints to make the tool sort of semi-automatic rather than automatic?
It's not a direction that we've explored largely for the purpose of differentiating from earlier work, because there are manual co-inductive provers already in existence that operate on languages like this. And the goal is to be distinct from those and be fully automatic. Although I will add that having a more robust lemma system would be beneficial in these situations.
Okay. I have another question. If there's, unless there's. Also, I'm curious why you're working so hard for rewrite rules, which is sort of a more rare feature in Haskell. So aren't there more common features that you could verify, like laws of type classes or quick check? So why do you consider rewrite rules so important?
Well, rewrite rules. Rewrite rules are they're a good way of characterizing the kinds of properties that we want to uphold, and that they're always formulated as equivalences. So that's amenable to reasoning with coinduction, and that, say, if you want to say, talking about arbitrary logical propositions, then like I said before, you need to say this function is equivalent to true, and when you have a formulation like that, you lose out on some of the benefits of a system that's designed for reasoning about non-strictness. Did I answer your question, or is there more to it than that?
Well, I mean, type class laws are also usually equivalences. Sorry, type class laws are also usually equivalences.
Yes, it's a possible way to apply these same techniques, but it's not one that we've explored directly.
What about other kind of algebraic data types, non-regular data types, or things like nests and bushes and things like that? Have you thought about those?
So, yeah, I don't understand. So, well, data types other than natural numbers and lists. Mm-hmm. That's what you're wondering about. Mm-hmm. Well, the Zeno suite consists principally of theorems about these lists and natural numbers and lists of natural numbers. But yes, there is. We have looked some into stuff like trees and other data structures like that, and generally this co-inductive approach does not. Well, it works best for properties or recursion follows a linear path. And so there could be some theorems you prove about trees, but it would require a different approach to have a more robust verification of theorems about trees, for instance.
Okay, so thank you again. So I think it's time to move to the next speaker. So let's thank John again.